Okay, so yesterday at 6.2, we talked about the fact that if I were trying to give every one of you a parallelogram and put it in your hands, we talked about all the features that should exist everybody's parallelogram, right? Even if your parallelogram is different than anybody else's, you should still have the features that your opposite sides should be congruent. Your opposite angles should be congruent. Your diagonals should be bisecting each other. All those facts are true regardless of the parallelogram that you're given. Does that make sense? Okay? Today, and tomorrow, the next day as well, I'm going to give you a quadrilateral. So up there on the board, I got quadrilateral, right? Okay? And I'm going to give it to you in the coordinate plane with those ordered pairs. And I'm going to ask you, is there criteria that you could determine that would tell me whether that thing is a parallelogram or not? Okay, because remember, parallelograms are special kinds of quadrilaterals, right? They have special features that make them different than just the general, basic, boring quadrilateral. Okay? So, we need some basically statements, properties, rules, theorems, whatever you want to call them, that allow us to determine some relationships that force it to be a parallelogram or to shed light on the fact that it's a parallelogram or not. Okay? One of them is really easy. One of them is the definition of a parallelogram. Okay? If I'm able to find slopes of all four sides, would that tell me whether that thing's a parallelogram or not? Okay, so I give you a quadrilateral. All right, now you don't have to write this stuff down right now. Just kind of watch. If I find that slope to be negative 0.5 and that slope to be negative 0.43, is that thing right now a parallelogram? Absolutely not. Okay, opposite sides have to be parallel for a parallelogram, and slopes have to be the same then, right? Okay, for lines or segments to be parallel, they have to have the same slope. But what if I do this? What if I take, let me just manipulate this a little bit. Is that a parallelogram now? Careful. It's, yes, we haven't shown that it's not a parallelogram, but we haven't shown enough information to show that, in fact, that it is 100% a parallelogram. By just showing these two slopes, on the top and the bottom, we've shown that bare minimum this thing's a trapezoid. Okay? We'll talk about that in the future, but I had to find that slope and that slope. And lucky enough, we see it, they're both 2. And now, is that thing a parallelogram? Yes. Yeah. So, later this week, when I say here's a series of ordered pairs, is this shape a parallelogram? That is an approach you could use. Okay? Find all slopes, and then make the argument that opposite slopes are parallel, or sorry, opposite slopes are same, therefore lines are parallel, and we're good to go. Does that make sense? But there are other approaches that you could use. I'm not saying the other ones are more efficient or less efficient. They're just different. So let's see some of these other approaches. One is the converse, and a lot of these are converse to what we learned yesterday. Yesterday I said if I have a parallelogram, the opposite sides are congruent, right? Both pairs of opposite sides. Here we flip the then of that statement. We say if both pairs of opposite sides of quadrilateral are congruent, then the quadrilateral is a parallelogram. Both pairs of opposite sides are congruent, then the shape is a parallelogram. Okay, so what that means to us is I'm going to give you, for instance, another quadrilateral. And if we want to use that theorem, we have to find distances, right? We have to find lengths. Okay? Do we have a formula from chapter 1? We use a little bit in chapter 2. We use a little bit in chapter 3 and 4. Once or twice in 5. That allows us to find distance in the coordinate plane? Yeah. Okay, so we'll use a distance formula to find that length there and that length there. And there we've shown opposite sides are congruent, right? Could I then find, and that's just one pair, I need both pairs. So I'll find that distance there and that distance there. And based off of that, we can now argue, we can make the conclusion that it is indeed a parallelogram. But the real reason why is because when those distances are the same, look what happens to the slopes. Are those slopes the same? Are those two slopes the same? Yeah. Okay. So, when both pairs of opposite sides are congruent, what happens is we default down to the definition eventually that you'll have opposite sides parallel, and then that provides a parallelogram. Okay. So that's one theorem, that's one approach we'll use. Okay. Another approach is kind of a combination of the last two things we talked about, and it's this statement. Here it says if one pair, you have to make sure you're paying attention to this, if one pair of opposite sides of the quadrilateral are both congruent and parallel. Okay? So only one pair of opposite sides, that's all you have to look at. You don't have to, maybe I just look at the top and the bottom, maybe I look at just the left and the right. It doesn't matter. Okay? If you look at one pair of opposite sides, and you're able to find the lengths of both sides, and you're able to find the slopes of both sides. Okay? And you get same slopes, and you get same distances, then you automatically have a parallelogram. Okay? What's nice about that then is it forces, and that's true, it forces essentially the same properties of congruency and parallelism on the sides that you didn't focus on. I'll kind of show you an image of that as you guys write that down, get it put together. And I'll go back to that in a little bit. And I kind of hate, I apologize, I don't know how to fix this, but I don't know if there is a way to fix it, but I hate the way they show slope on GeoGebra. But what I'm looking at right now is the blue sides. Okay, I just picked a set of sides, and I look at the slope of the blue sides and the lengths of the blue sides. And the length of the blue sides are 4.12 and 6.32. Are those the same? No. So can this thing be a parallelogram? No. It's just a basic quadrilateral. But let's see if we can adjust those lengths so that they are the same. So let me move some things around here. Try to get maybe both of them to be 4.12. Okay. So I get 4.12 here, and I get 4.12 there, right? What did that do to that slope of that blue line on the left and the slope of the blue line on the right? Made them the same, right? So right now we see that we have one set of opposite sides, congruent and parallel, right? Well, let's see what that does to the parallel or the quadrilateral in general. If I have this red side and that red side, they're both horizontal, right? Are any two horizontal lines that have a slope of 0? So that means they're parallel, right? Any two horizontal lines are parallel. Let's find the lengths of those. Both 5, right? Okay. So just looking and determining that the blue sides were both congruent and parallel. forces the same properties on the red ones, okay? And if I can force parallel, if I know the blue ones are parallel, okay, and congruent, that forces the red ones to be parallel, then I've got both pairs of opposite sides being parallel, right? Okay, it classifies that thing as a parallelogram. Okay, so that's a very useful theorem. Okay, I don't know in regards to the amount of math that we'll go through in the coordinate plane. I don't know if that will be any more efficient or less efficient than other approaches, but it's an alternative approach. Okay, sometimes in the homework that you see in your math Excel tonight, that might be they might give you a picture and they might only be giving you expressions for opposite sides. Well, then you have to use maybe this theorem. Okay? So depending on the amount of information that you're provided with, you might kind of delineate down to, focus on this theorem or theorem A in contrast to maybe theorem B or C. Okay? This one is a little bit harder to do in the coordinate plane because it talks about angles. You guys remember talking about sine, cosine, tangent stuff last year? Okay, we're going to do a lot more of that this year. Maybe February-ish. But it is really hard for us right now. And even after we start talking about it in February, it's going to be very difficult for us to find angle measurements in the coordinate plane with the tools and the math knowledge that we currently have. Okay, my trig students, my college algebra students, my Mr. Haynes, physics students do this a lot, but it's kind of outside the scope of our course. But in Math Excel tonight, when you're not working the coordinate plane, and you're just trying to apply and learn these theorems, you might have to use this one. It says if both pairs of opposite angles of quadrilateral are congruent, then the quadrilateral is a parallelogram. That's a converse of what we said yesterday, right? Yesterday, said if we have a parallelogram, opposite angles have to be congruent, right? Now, the key thing is that both pairs have to be congruent. Both pairs have to be congruent. So let's see something that looks like this. All right, so if I give you that picture, are either set of opposite angles congruent? No. Okay. But let's say I start manipulating this thing and changing around a little bit. Let's say I do that and that. And maybe, let's do it this way. Let's go. I was thinking someone else, that was a trapezoid. Let's go this way. Do we have a pair of opposite angles there that are congruent? Yeah. But do we have both pairs of opposite angles congruent? No. So one pair is nice, but one pair does not create a parallelogram, right? Because there we get one side AB to be 0.5, and then the opposite side DC to be 0.2. So that's not a parallelogram. Does anybody know what that is? That's a kite. Okay. What we need to do is we need to take that kite and move things around a little bit so we get something that looks kind of like that. And now are both pairs of opposite sides congruent? Or sorry, both pairs of opposite angles congruent? Yep. And now we see that AB and DC are both parallel, same slopes. And then here, I get those slopes. Okay. Still the same. Negative 0.5 and negative 0.5. So okay. Is that doable? Okay. Let's see here. Kind of running out of time. If an angle that's both of its consecutive angles are supplementary, then the quadrilateral is a parallelogram. If an angle is supplementary to both of its consecutive angles, it is a parallelogram. What this statement is getting at is kind of this object, this idea. I don't know, I'm kind of moving fast here, we're running out of time. If I look at the red angle, would you agree that the two green angles are consecutive to it? Okay. If I look at the red angle, okay, and maybe angle B up here, okay, so I focus on those two angles. Would you guys agree that if we were to extend the lines, things start looking like that? And is that a familiar type of shape or image that we've seen in the past? Parallel lines cut by transversal, right? And we knew that if we have same side interior angles and they add up to 180, what's that tell you about these two lines? They should be parallel, right? Okay? So that idea right there, looking at those two angles being supplementary, forced the kind of the vertical lines here to be parallel. Okay? But that doesn't guarantee enough to make sure that this thing is a parallelogram. We then have to look at these two angles. Okay? If we look at those two angles, are they same side interior for that line, and this transversal? And are they supplementary? So that makes the top and the bottom parallel, correct? Okay. What I want you to understand is that you have to have both. Because look at that. Are these two supplementary? Those two are supplementary, right? So that makes this segment and that segment, it makes those parallel, right? Is this angle and that angle, are they supplementary? No. So that means that those lines are convergent. They're not parallel. Okay? What type of shape is that then? That's a trapezoid. Okay? So to be a parallelogram, we need both pairs of opposites. Both pairs of consecutive angles to be supplementary. One more theorem. I know we're out of time. I apologize. We know yesterday that the diagonals bisect each other, right? So here, if I give you a quadrilateral and you're able to measure the diagonals, okay, or use the distance formula to determine diagonals and determine essentially the four parts of the diagonals when they intersect, and you find out that they're being bisected, okay, you have a parallelogram. Okay? In your homework tonight, you're going to see things like this. You're going to see a question like that. They're going to say, find the values of x and y that force that to be a parallelogram. So what do I do with y and x plus 2? 7 equal. Opposite sides have to be equal, right? What would I do with 3x minus 5 and 2x plus 1? 7 equal. And I'll be able to solve those equations and solve for x and y, so that forces that thing to be a parallelogram, right? You'll then see questions that ask you something like this. Now it's talking about angles, right? So what do you need to know about like angle H and F? What would they have to be to one another? They have to be equal, so there's an equation, right? What's that also tell you E and G have to be? Equal, so there's another equation. What about F and G? What would they have to be to one another? Supplementary, equal to 180, right? But F and G are equal to 180. No, what has to happen between G and H? They have to equal 180 as well. So that will help you get through this evening's homework.